We structure our analysis around applied real-world problem, but it's reduced or abbreviated form to get it done in the 15 weeks. And we're going to create some data and condition it. That'll get you to both work with geometry and also with tabular data. And then we're going to identify a workflow. So we'll create these data for a small area and identify a workflow for a large area. So I'm going to give you a complete data set after you've gone through the development of the data for a sub area. The point isn't to have you spend all your time digitizing, but to refresh those skills and to see the connection between the data that you create and the analysis you're going to do. We're going to calculate watershed flow for a couple of watersheds under base conditions, and then we're going to modify the data, modify the landscape to achieve zero runoff. Now, this is an important problem that a lot of cities are struggling with, both because of increased urbanization. More pavement means more runoff and more people getting flooded downstream that didn't used to get flooded downstream, and also because of climate change. We're getting wetter, more intense storms, and so we're getting more flooding due to that. So folks are having to deal with runoff. A lot of municipalities require new subdivisions to capture a 1 or even a 2-inch storm before they generate appreciable flow to the storm sewer mains. We're going to practice building these databases over the first 4 to 6 weeks. We're going to calculate runoff at key locations and propose modifications and calculate costs. Now, the cost calculations come mostly from tabular data. The proposed modifications come from reanalysis of modified landscapes. We're going to add canopy and add impermeable surface, that is, surface that allows water to infiltrate, and look at green roofs or underground storage. All things that the city of St. Paul, Maplewood, Woodbury, various other municipalities have entertained in the last 5 to 10 years in managing water. So today I'll review the problem and the extremely simplified rainfall runoff model we'll be using. Most analyses have some model of how a system functions if you want to get data for some decision, and we have to identify what that model is. Then we're going to practice creating data and calculating runoff various times. There are several iterations in this analysis, so we'll define a workflow and learn Model Builder to aid with parts or all of that workflow to be able to redo that. Model Builder is a ArcGIS/Esri utility that allows you to automate workflows or sequences of operations with data. So what's our model? We're going to calculate runoff after rainfall was intercepted by the canopy or infiltrates, or we'll say absorbs, so interception and infiltration, don't get confused, absorbed into the ground. So we have rainfall that comes down directly onto the surface or that hits trees and comes down as throughfall, so it's reduced, as indicated by the smaller blue arrow here. If it's a hard surface, we're going to assume it's all runoff. If it hits a soft surface, so anything that's not concrete, asphalt, or a building, we're going to assume that a portion, perhaps all of it if it's small enough rainfall or large enough absorption, a portion goes into the soil and a portion runs off. And again, it could be zero that runs off if the rainfall is less the absorptive capacity of the soil surface. So we have this gross rainfall minus canopy interception gives us throughfall minus whatever gets absorbed between where it hits and this accumulation point. In this case, a sewer grate, which we'll call a pour point or a watershed outlet, is the total over an area. So gross rainfall, canopy interception, throughfall, a certain amount lands on the leaves and is stuck on the leaves. If you've ever been in a forest and it starts raining, you don't feel the first raindrops, or at least with all its intensity, until there is some absorption by the canopy and the canopy saturates. In arid environments, the canopy can absorb of the total rainfall up to a third of the rainfall, especially if the rainfall falls in light, gentle events as opposed to torrential downpours. Someplace like the Pacific Northwest, in Seattle, a large portion of the rainfall gets absorbed by the canopy and then gets re-evaporated without ever reaching the ground. So there's gross rainfall and then throughfall. Now the throughfall is the net rainfall. It hits the surface and some goes in, and infiltration, or what we'll call absorption. The rest runs off into channels and then flows to the outlet. We're going to make a pretty simplifying assumption here. We're going to assume that this absorption is uniform across a soil surface. So if we map a soil type, there's an infiltration or absorption amount. And anything beyond the absorption gets transferred into runoff. So the net rainfall, which is rainfall after the interception, if that's less than infiltration capacity or absorption capacity, then the runoff is zero. If it's greater than the infiltration capacity, then you'll get some runoff. I guess the dog is full now, had its drink. We're assuming that this rainfall makes its way, runoff makes its way to the outlet. And so we have to sum the net runoff over our watersheds. You got to remember the water volume is the amount or depth of runoff times the area. And we're going to break our watershed up into units that have uniform runoff, and then basically sum across the watershed for each of these units the volume of water to get a volume that's output, a net output. So we have this equation which is runoff is equal to the rainfall minus the canopy interception minus the soil absorption. And you can do that on a polygon by polygon basis or a cell by cell basis. And then multiply by the area of the polygons that have a uniform R minus C int minus abs, or on a cell by cell basis, do this R minus C int minus abs. We can do this calculation in vector or raster, and indeed we will do both. Also, why is this a difficult problem? Largely it's because it's a difficult measurement problem. Right? How do we get estimates of canopy interception or soil absorption across the landscape? What data layers do we need? What attributes, categories, or values do we need for those layers? Well, clearly we need canopy mapped across the landscape. We need surface type. And where the surface isn't a hard surface, we need the absorption capacity across the landscape. So we need to create all those layers or find all those layers and the appropriate values. Right? And I've already said that, right? These aren't uniform across the landscape. So you can see here, this is a watershed. And across that watershed, we have a canopy that varies, surface that varies, and even within the surface that's exposed, lawns or other areas, there are different amounts of interception and absorption in these areas. So we are going to avail ourselves of the literature to get canopy absorption measurements. A lot of work has been done underneath canopies of various types, measuring the amount of through flow. So you can measure the amount of water or rainfall you get outside of the canopy or above the canopy, and then the amount you get below the canopy, and do a simple subtraction. And calculate then for the growing season or for an individual storm the gross rainfall and the throughfall, and this has been done. We're going to avail ourselves of those. Folks have also measured the amount of infiltration capacity in various soil types and mapped those and associated those with soil types. So we can do that also. We're going to then sum those across the landscape. Now we're going to make a simplifying assumption here. We're going to assume that any water that lands on a hard surface makes its way to the outlet. We're not going to concern ourselves with interflow absorption. In real life, that's not true. Water will land on a hard surface and flow off onto an infiltrating surface from a sidewalk to a lawn, and they will get some additional infiltration. We're not going to do those sorts of calculations. They're too involved here. We make this assumption because it's a first approximation, It allows us to get a ballpark estimate, a reasonably good estimate. And this is the sort of thing that would happen before additional analysis that's more involved. Typically, they'll do a simplified analysis like this to get an idea of the magnitude of the problem and where you have to expend more resources for a finer analysis. So we'll be mapping across the landscape, digitizing the canopy. And we'll be digitizing the canopy by different categories, height categories and species categories. It ends up the surface area of conifers, because of the needles and the needle shape, is much greater than the surface area of broadleaf species in the same canopy. And the taller the trees, the larger the canopy volume, the more interception you get. We're going to have 4 categories of large and smaller, tall and short, conifers and hardwoods, and that creates 4 different categories of interception. We'll assume interception is uniform for those. So we'll have the gross rainfall and we'll subtract the amount of interception as a function of those 4 types to get a through-fall layer. Once we have this canopy interception layer, we can subtract it from a rainfall layer and give us then a net through-fall layer. So we build the rainfall and canopy layers and do the subtraction. Now, once we have this through-fall minus the absorption, how do we get to the absorption? So we want to get runoff, and we've calculated the through-fall. We have to then subtract the absorption. And we'll use simplified calculations that are based on surface type, where the absorption is 0 any place we have concrete buildings or asphalt, and it will be a soil-specific value wherever we have an absorptive surface. So that means we need maps of these things, where we have concrete buildings or asphalt, and maps of the soil layers. So we'll build these. We'll digitize buildings and then land cover. We'll get a pervious, impervious surface for the non-building areas, in this case, roads or parking lots or sidewalks or other structures. And then we'll overlay those to get a pervious, impervious total layer. You can then combine those so that we have this max absorption layer where it's 0, where we have all those impervious surface, then a soil determined value shown by these differences in colors. And so then I have a layer that is my through-fall and a layer that is my max absorption. I can minus one from the other to get the net left, which is runoff. But we have to be careful of negative runoff outputs. If I have a rainfall that's less than the canopy absorption, I would get a negative value. But you can't have negative values in the runoff because it's either 0 or a positive value. It's not like this is an extra absorptive area in the canopy because it could have absorbed more than it rained. Similarly, if I have a soil infiltration or absorption value greater than the runoff for that location, for that instantaneous spot of input, I'm not going to have a negative amount. And so I wouldn't want to balance within a watershed positive runoff with a negative in another area. Now, in real life, if we were to consider the horizontal transfer, then we would have to do a third step, and we wouldn't look for negatives until we transferred the water across the surface. But we're not going to do that. We're just going to do a simple space-specific algebra here. So to solve this problem, then, I need the rainfall, I need the interception, which means the canopy by type, I need the absorption, which means those layers, and I'll build these, and I'll sum over the appropriate watersheds. So we also have to calculate our watersheds and then do that sum. And that's really our work for the semester. We'll do that several times because if we have a positive non-zero runoff value, we'll then modify the surface by adding more canopy digitally, by changing the permeability of roads or sidewalks. You can actually build impermeable or permeable roads. Permeable road is much more expensive, but it absorbs water at almost the rate of the underlying soil. The same thing for parking lots. You can add things like green roofs to the tops of buildings, or you can build underground storage, large underground structures that basically have a gravel bottom open to the soil, and they fill and contain the water and let it slowly percolate. And these are dreadfully expensive and to be avoided where they can be, but Seattle, New York, Chicago, almost all big cities have had to avail themselves of these to reduce flooding, within their boundaries. And so we're going to do that for a 2.5 and a 5 centimeter storm under current conditions, calculate the runoff volumes, and then modify the landscapes to reduce the runoff for our watersheds to zero using a set of treatments. Once we've done that, we have to calculate the costs of those treatments. And that's our semester in a nutshell.